Well, good afternoon. My name is Ivancich. I work for IBM. I've been working on Ceph for a bit over a decade. Initially with a startup called Cohort FS. We were acquired by Red Hat in 2015, I believe, but we'd been working on Ceph prior to that. And then, of course, IBM acquired Red Hat, and since January 2023, our team, the storage team, has been moved from Red Hat over to IBM. So today's talk is on ordered bucket indexes or ordered bucket index shards in RGW. And I'd first like to go over a few basics on bucket indexing and resharding. RGW maintains a series of objects that contain the metadata for buckets. There is the bucket entry point, which is we use the name of the bucket in order to reference that. That in turn points to the current bucket instance object, sometimes called the bucket info object. And from there, it has all the information that we need in order to access all of the shards that go with that particular bucket. If you have n shards, they're just simply numbered from 0 up to n-1. All right? Now, those of you who have used RGW are pretty familiar with the idea of resharding. And that is there's a limit on how many entries we can put in each of the shards. It's about 100,000. And so when we need more to have more entries than that, we need more shards. And so we basically resplit things up into more shards through this resharding process. In general, we can store 100,000 objects per shard. That changes a little bit with version buckets. And when the number of objects divided by the number of shards for a given bucket exceeds a certain threshold, that will trigger dynamic resharding in order to split it up into more shards. And more recently, about I think two years or so ago, we added the ability for dynamic resharding to actually shrink the number of shards as well. So if you're not using all your shards to their full extent and you have some extra space, they can actually shrink them up as well. All right, resharding this is how it used to be done. When we wanted to reshard a given bucket, we would lock down the bucket so there's no writes that could occur during that period of time. We would then create a new bucket instance object and copy the data from the old shards into the new shards. And as the final step in order to commit that, we would then have the bucket entry object refer to the new bucket instance object. And then we would allow writing once again. Now, there have been some recent changes, and this was done in order to better support multi-site, in that we no longer create a new bucket instance object every time we reshard. Instead, all of the shards have a generation number built into their object names. And we simply keep a record of all the generations of the resharding schemes in the bucket instance object. We create the new set of shards, and then we update the existing bucket instance object to refer to all of those. Now, currently we use something called hashed bucket index shards. And this has been done since the inception, and I think I saw Yehuda in here someplace. I'm sure he's the one who ultimately implemented this a while back. But we take the object's name, we run it through a hashing algorithm, and then we use the modulo operation to figure out which shard that object goes onto. Okay? There's some really nice advantages to this particular technique. The shard number is calculated in a constant amount of time, and all we need to know is the number of shards and the object's name. And generally, it distributes the object names across the shards relatively evenly. That can change under version buckets, but in the unversioned case, it tends to spread everything out relatively easily, which has other advantages. There's some disadvantages, potentially. One is that resharding is a global operation. We have to lock down the bucket, create a whole set of new shards, copy the information over, and then commit that operation, and then allow writing once again. There's been a recent contribution to the RGW side where we now actually divide resharding into two phases. In the first phase, we still allow writing to occur to the bucket. And it's only in the second phase where we disallow that when we finalize the new data structures. Okay? The other disadvantage is that bucket listing is a very intense, IO-intensive and complex operation. So what we do in the RGW, and I have I guess a laser here, we copy a batch from each of the shards. Again, there's no ordering among the shards, so everything is really scrambled in there. But we download a batch from every single shard, and we use a selection sort to output each object in its lexical order, all right? Once we exhaust any one of the batches, we then go back and ask for a batch once again from each and every shard and do the process again. Now, because the objects tend to be distributed across those shards evenly, we tend to consume those batches for every cycle relatively evenly. So it works out pretty well. And again, the one case where it doesn't work out so well is with ordered buckets. We'll kind of get into that a little bit. Wait, did I go the wrong way? I think I did. All right. So in order to address some of these issues, for a while now, we've wanted to be able to have ordered bucket index shards, okay? And the key difference is that we're now going to maintain the lexical ordering across shards. All right? So again, we have the same basic data structure we've seen previously, but now all of the initial object names lexically appear in shard 0. The next batch go to shard 1, and so forth. Which means when we want to list the objects in the bucket, we can simply walk through the shards one by one and display them, okay? It gets rid of all that complexity with that previous listing algorithm. And the way we're going to do this is we're going to use something called the OMAP in the bucket instance object. That's a key value store, and the keys will be the cut points of where the divisions are between the shards in their lexical and the object names that are lexically ordered among them. All right? And the data in the map will contain some additional value information, including what the name of the object for that shard is. So, what are the advantages here? Bucket listing becomes much less IO intensive because we're no longer retrieving batches from each shard. We're simply walking through the shards one by one. The other advantage is that resharding can become a local operation. We no longer have to reshard the entire set of shards. If one particular shard crosses a certain threshold as far as how many entries are in it, we can then split that into 2, 3, or more shards and spread those out. And likewise, if there's a consecutive set of shards that have very few entries across them, we can join them together into a single shard. All right? So when we need to lock things down for resharding, we only have to lock down a few of the shards and not the entire bucket. All right? Now, there are some potential disadvantages with this. The first one is that there are certain workloads which could create these things called hotspots. If you imagine a workload where the object names are come in the same order as the lexical ordering, it means we always want to write new data to the last shard in that sequence. And that shard then becomes the focus of a lot of the write operations. All right? So that's one potential downside of this. The other disadvantage is that it's much more complicated now to calculate which shard a given entry goes onto. Before, we just needed to know the number of shards and the object name, and we could do it in constant time. Now, we're going to have to consult the bucket instance object and find out which shard that particular object entry goes onto. Now, we hope to mitigate a lot of this by caching some of that information, so we don't have to do a read each and every single time. Okay? Version buckets create some additional challenges. For those of you who attended Yehuda's talk earlier on what's the name? Snapshots. He discussed that to some degree already. All right? There's a constraint currently, which is that all the versions for a given object have to appear on the same bucket index shard. All right? That's done for some reasons, but the primary one is that we want to be able to modify multiple entries in there at the same time atomically. If we had to do that across multiple shards, that would create further challenges in making that happen in an atomic format. Now this undermines that even distribution across shards that we want to have in the general case. And so bucket listings that include versions become less efficient because if you think about the hashing indexing scheme, we may not be reading across those batches evenly. We may have to go through a lot of the versions for one particular object and exhaust that batch quickly, and then go back and read more batches from all of the different shards. So that's kind of the downside here. And there are some corner cases where there could be more than 100,000 entries for a given object, versions on the same shard. And so resharding becomes challenging. We may not be able to get it below 100,000, which is our soft limit, the point at which warnings start taking place. All right. So we're hoping, although we're still in the design team is still kind of discussing how best to implement this, but we would like to be able to improve that as well. So for a version object, the number of entries we need in the bucket index object is 2 plus 2n, all right? And so if you think that we could have ultimately 100,000 entries on a shard, that basically means that if all of the versions of a given object exhausted the entire shard all to itself, we could have about 49,999 versions, and that would be the upper limit before warnings start occurring. We are looking at ways to address this. I don't have anything to say much on this right now. It is challenging given all the other constraints, but we are trying to figure that out. What's the status? It is a work in progress. Prior to embarking on this, I did a simulation to make sure that certain aspects that as I imagined them would work out. So I wanted to make sure that we had a new shard naming scheme that could replace the existing one that would allow for insertions and joins, or splits and joins. And I also wanted to verify that we could lock things down minimally as we're writing into a bucket so as to minimize that performance hit. Okay. Diving a little bit deeper into the shard naming scheme, with hash bucket indices, we simply have some sort of prefix, and we put .0 for the first shard, .1 for the second shard, all the way up to n-1. So all we have to know is the prefix and which shard number, and we can generate what the name of that object is. Now, because we're going to allow splitting and joining, we can't do that. And so we're going to use instead a hierarchical naming scheme where we have a prefix and we start like at 64,000 to allow it to grow in both directions, get lower and also get higher. And then we simply create new object names which are numerically higher or lower than the ones we already have in order to insert new names in there. I wanted to test this out to make sure that we wouldn't end up with 100 different levels of indexing. And so I tried various naming schemes where the names would go up monotonically, they would be distributed across a uniform range, they would be follow a normal curve and a shifting normal curve, and even also reverse monotonic and reverse shifting normal to see how this naming scheme would operate. And in the simulation, I put a lower limit on the number of objects per shard at 200 just so we could get more splitting and joining. We added 10 million objects across 10 threads. And then I removed about half of the objects in another thread where 1 out of 1,000 objects would be eligible for removal. And we would remove it plus the next 500 objects as well consecutively in order to empty out shards so we could then test the joining aspect of the algorithm. And the results came out pretty well. So the mode is about 4 levels deep on the hierarchical naming scheme. There are very few that got up to 9 levels deep on that. And that's because we can reuse those names. Once we split and join and stuff, higher levels in the hierarchy become available for use. All right. Expected availability, we're aiming for a minor release of Tentacle to have this available, and downstream in RHCS 9.1. And that's basically the talk. Are there any questions? Yes. Oh, excuse me, would you mind they ask to go to the microphone so that can be part of the video?
So the way, wouldn't you have a lot of entries into the bucket index or bucket instance object?
So yeah, we can have about 100,000, that's correct. So we could refer off to 100,000 shards, if that's what your question is.
Okay, I thought you said there's an entry for every name, so we can do that mapping. So
We don't map every single name into the bucket instance object. We only map the cut points in there. So where
Gotcha,
one
okay.
shard ends and the next one begins, because that's all we need to know.
yeah, that's what I was confused about. Perfect.
Okay. Other questions?
So at the beginning you showed that it used to be done in the way that when we're doing resharding, bucket was just frozen and we made like copy, and then when we made a copy we just updated the link to it or something
Yes,
like this. Yeah. But which version undergone from this way transition? In which version we undergone the transition from this way to more flexible? Because, for example, now we are running 18:4, and like when we're doing resharding, we see the freezing for some objects, but it's not for all bucket. We can continue working with it. Like, which version did you describe this transition would go of Ceph?
I'm not positive. It's probably been about 2 or 3 years. I don't know if you know, Matt, specifically. Got it, okay. So, so yeah.
Okay.
So bucket listing, I assume, is now just going to whichever shard you start with a listing key and goes iterate one by one.
Say the first part again.
Bucket listing.
Yes, uh-huh.
So there's no concurrency anymore in bucket listing?
Concurrency as far as IO
fetching-
reading?
fetching.
No, there doesn't have to be. I mean, there can be. You can prefetch the next shard if you'd like. But no, we're just kind of reading one by one and reading off each shard one by one. Yes.
Which is fair, just it might have some performance implication in certain cases.
Perhaps, yeah. But I think in general, if we have thousands of shards and we're using the existing algorithm, that has I/O
Oh,
implications
for sure.
too. Yeah.
It's not comparable.
Right.
Did you say the bucket instance object only holds 100,000 shards?
So the OMAP for any object in Ceph is limited to 100,000 key value pairs.
Okay.
So-
with 100,000 in the bucket instance object and 100,000 for each shard, that limits number of objects per bucket to 10 billion?
So yeah, if we're doing 100,000 shards and 100,000 objects per shard, yeah, then it's 10 to the 10th. Did I get that right?
I think so.
So,
Okay.
Is there a strategy for that?
when you say strategy, what do you mean?
People don't like large or bucket size limits, so is there a strategy for getting past that 10 to the 10?
There, yeah. So with what I described, no, that would kind of be the upper limit. There are some ideas that I have been playing with, but those will not be part of any initial implementation. I can kind of give you a brief view of those. And again, we're not sure if we're going to need this, but there is this idea of having a hybrid bucket indexing scheme that combines the ordered and the hashed. So we divide the shards into blocks. And the first block is lexically ordered before the second block, and the second block before the third block, and so forth, okay? Then within a block, we would use a hashing scheme to divide objects between those, all right? Now, this helps address, first of all, the hotspot issue in that different objects will go onto different shards within a block. But the other advantage here is that as far as the bucket instance object goes in the OMAP, we only have to maintain the cut points between the blocks, not between the shards. So now we can expand that space even further as well. But again, this will not be an initial implementation. That's just something that we have in our back pocket if we need it. Other questions?
So this will take place in Tentacle, the change in logic, right?
Yeah, so that is our goal, is to have a subversion of Tentacle, yes.
So-
Tentacle.
Buckets created prior to Tentacle, is there any sort of migration that you have to do of the bucket?
So there already is a RADOS-GW admin command to reshard a bucket. So the expectation is that there'll be another option to say which sharding scheme you want to reshard to, and you can reshard from the hash indexing scheme to the ordered indexing scheme. Additionally, we expect there to be a configuration option as what the default is. So when you create new buckets, do they come out as hashed or as ordered? And there may be some use cases where hashed actually is better.
I may be missed, but could you please let me know how cut points are determined?
The cut points,
Yeah.
they're determined dynamically. So we'll start up with a certain number of shards, and we'll start putting information or object entries into those shards. At some point, a given shard has enough where we want to say we should split this, all right? So we will decide, if we're splitting into two, we'll go halfway down the middle, and that will be the cut point between the two new shards that we get out of the splitting operation. All right? And it will just keep on splitting again and again. And likewise, when we start joining shards together, if that point ever comes, we will know the split point between the newly joined shards and what preceded and what followed.
Okay, then at first, only a few of bucket shards will be used. Is it correct?
Yeah, so I don't know exactly what the optimal value is at this point. With hash bucket indexing shards, we start off at 11, unless multi-site is in operation, in which case I forgot what we start off with if multi-site is in use. We start off with even more shards, though. Just because sharding is expensive in the multi-site environments, we want to start you off with more shards to work with.
Okay, thank you.
You're welcome. Other questions?
Yeah, just about CPU usage using ordered buckets. Do you have any, I know you said you haven't done much benchmarking yet, but do you have any kind of like CPU usage metrics about the difference between, hashing is very easy, right? And
Right.
ordered buckets, it's a lot of sorting. Yeah.
So the sorting is going to come out of the process. So once we have an object name, we want to find out which shard it goes to. In the worst case, we do the OMAP lookup on the bucket instance object, and it'll say, this goes to this particular shard. And it goes into the OMAP there. And then OMAP is backed by RocksDB, and that orders things automatically. And they're already ordered that way with the hashing scheme. So when we get a batch from every single shard, we're getting a batch starting at a given marker, and then we ask for, say, 10,000 or 1,000 objects from that point. And so that's already part of the process. Matt, I don't know if you want to go to a mic.
The CPU cost is going to be net equivalent. The difference is that insertion and deletion is going to involve logarithmic time operations, but it'll still, but the sequential operations are going to be cheapest for listing.
So right now, what we suffer from, and everyone does, is with RocksDB is handling all the compactions because of people deleting stuff and all that changing. So is this going to actually increase the amount of RocksDB? Because RocksDB is doing the self-ordering. Every time we do an insert now, it's insert ordered. Do we see an increased potential for having to constantly be compacting on?
I don't have a good internal model of how that works. I know there are some core developers here, Sam, who can answer that.
OMAP is always ordered. So the shards you have there, same thing. They'll probably be smaller though, which is good.
Another question. How do you identify the midpoint of the OMAP? Is there an OMAP operation for it, or do you track it somehow?
The midpoint within an OMAP. I don't think there's an operation for that, a CLS operation for that. So I think we're going to have to scan the entire shard. Am I understanding your
Sam?
question correctly? So you're saying when we do a split?
Yeah.
So no, there is no magic operation for that, but you could definitely write a class operation for it.
Okay,
You'll still have to do a scan,
yes,
but you could do it on the OSD.
got it. Other questions? All right, well, thank you very much, and you're welcome to ask me any other questions outside the meeting here.